Welcome back, AP Environmental Science. Here we go, human health and environmental risk. The truth is that most people face some sort of environmental hazard every day. The hazards we may face can be voluntarily um, exposed to, or we make a decision to expose ourselves, like smoking tobacco. Or they can even be involuntary, where we could be exposed to air pollution. So, when assessing the risk of different environmental hazards, regulatory agencies and environmental scientists and even policymakers use a three-step risk analysis process. It's risk assessment, risk acceptance, and then risk management. And so we're going to discuss and examine these three steps. So after this risk analysis lesson, you'll be able to explain the process of qualitative versus quantitative risk assessment and understand how to determine the amount of risk that can be tolerated, and discuss how the risk management balances potential harm against a lot of other factors that you may not be thinking about. Um, in contrast, the the innocent until proven guilty principle, when it comes to being precaution or showing precautionary. I didn't say that right. Contrast the innocent until proven guilty principle and the precautionary principle. So there's these two different principles that we use to evaluate our risk assessment. As illustrated here, risk assessment is the first of a three-step process that involves risk analysis. And so risk analysis seeks to identify a potential hazard and determine the magnitude of the potential harm. There are two types of risk assessment. There's a qualitative and a quantitative. And each of us has some sort of idea of a risk that's associated with different environmental hazards. But the purpose of an environmental hazard is anything in our environment that can potentially harm us is proposed to be an environmental hazard, essentially. So environmental hazards include substances like pollutants, even other chemicals or contaminants, or even human activities like driving cars or flying in airplanes, or even natural catastrophes like volcanic eruptions and earthquakes. So all of these things can be an environmental hazard. We generally make qualitative judgments in which we might categorize our decisions of having low, medium, or high risk. And when we choose to slow down on a wet highway or to buy a more expensive car because we feel safer in it, then we're making these qualitative judgments of our risk. And we're basically evaluating risk in a very variety of ways. So we make judgments that are based on our perception, but we're not actually doing that based on like actual data. So it would be unusual for us to consider the actual possibility that there's a statistical likelihood of an event occurring, and also there's a possibility that an event can cause harm to us. Because our personal risk assessments are not very quantitative, we often do not match the actual risk that's really involved. So, for example, some people, they find air travel very stressful, and because they're afraid to like fly in a plane or that the plane might crash. At the same time, some people prefer to riding in a car, and they can perceive that as much safer. Another person may be very cautious about safety while walking in an area with a heavy traffic, but consider like the health hazards of, smoking or all of that, or lack of exercise. So there's a lot to consider here. To manage our risk effectively, we need to ask ourselves, how closely are our perceptions of risk matched to an actual like real data and the reality of that risk. In the U.S., the probability of death from various hazards can be calculated from data that is kept, and it's fortunately kept by the government. But looking at the total number of people who die each year and the cause of that death, essentially researchers have been able to determine the probability of an individual and how they will die from that particular cause. So here we have a diagram which provides current data on causes of death in the United States. Because these risk estimates are based on real data, they are quantitative rather than qualitative. And if we examine this figure, we can see that the probability of dying in an automobile is far greater than the probability of dying in an airplane. It's also similar to the probability of dying from heart disease. It's monumentally greater than the risk of dying from a pedestrian accident in the city. These numbers that are underscored here. Uh, those those are perceptions of risk, and they can often be very different from the actual risk. So, like, because a catastrophic event like a nuclear power plant meltdown or plane crash, they can do a great deal of harm to humans in general. It receives great media attention, and people behave like it's really risky to use all of this kind of stuff. And it's like nuclear reactors are bad, but when you consider it to flying in airplanes, what what is the real risk? As the events of like a nuclear reactor, they rarely occur, and so the risk to actually harm humans is really quite low. Um, in contrast, we tend to downplay the risky activities that provide to be very harmful. It's usually a cultural thing or a political or economic thing, like drinking alcohol or working in a coal mine, for example. You can be like, oh no, can't work in a. It's normal to go have a drink or to work in a coal mine, but if you look at that, that's actually how people can really die. So qualitatively, there's some cases of death that people perceive as having a high probability of occurring, and then there's also, in contrast, there is uh, another belief that there's a low probability of occurring, like dying from heart disease, which is actually you actually have a very high probability of actually dying from heart disease and from cancer. Oh no, let's not spray that or do that because it causes cancer. When in actuality, 1 in every 7 people, based on our 2012 data here, will die from cancer. And I think at breast cancer, at this point, we're up to 1 out of every 3 women will have cancer. I mean, the reality is if you live long enough, you will die of heart disease or cancer. I wonder what the probability of dying of old age would be. What do you think, Landon? What's the probability of dying from old age? If you live old enough, you have a 100% chance of dying from old age. In fact, you have a 100% chance of dying, period. So the most common approach to conducting quantitative risk assessment is expressed in a simple equation. So the risk equals the probability of being exposed to that hazard multiplied by the probability of being harmed if you're exposed to that hazard. So using this equation, we can ask whether it is riskier to fly on a commercial airplane for 1,600 kilometers or 1,000 miles per year, or if it's riskier to eat 40 tablespoons of peanut butter, which can contain tiny amounts of these carcinogenic chemicals that are produced naturally by a fungus that sometimes occurs in peanuts, or often actually occurs in peanuts, and then they're used to make peanut butter. So the risk of dying in a plane crash depends on the probability of experiencing a plane crash, which is actually very low. But if you multiply that by the probability of dying if a plane does crash, it approaches almost 100%. So the risk of dying of cancer from consuming peanut butter depends on your probability of eating actual peanut butter, which may be 100%. And if you multiply that by the probability of consuming peanut butter, that will cause you to develop like a lethal cancer, which is very low actually. So it turns out that both behaviors produce a 1 in a million chance of dying. So this example demonstrates a fundamental rule of risk assessment in that the risk of a rare event that has a high likelihood of causing harm can basically be equal to the risk of a common event that has a low likelihood of causing harm. So quantitative risk assessment brings together tremendous amounts of data, and they're estimates, right? Estimates of harm, and they can come from like acute or chronic dose exposure response experiments or retrospective studies or prospective studies. And these estimates of which concentrations of chemicals in an organism will experience in the environment incorporates the concentrations found in like nature or even just like routes of exposure. Also considering solubility and persistence and the potential for a chemical to bioaccumulate or biomagnify, something else to consider. So altogether, these two groups of data, quantitative and qualitative, can be used to determine or to estimate the probability of harm. Okay, I know I've talked about this before, but there's a case study in risk assessment I want to share with you. We've talked about the water pollution, it was earlier in like the 1940s or 1970s, where companies just manufactured electrical components. They dumped all of these PCBs into rivers, that polychlorinated biphenyls that we've talked about. So at the beginning in the 1960s, there was an increase in evidence that these PCBs might have harmful effects on organisms that came in contact with them, and that included things like liver damage in animals and impaired learning development in humans. So once the EPA identified that PCBs was the potential hazard, it began its risk assessment, and so the agency brought together a range of data. Scientists had to determine which concentrations of PCBs might actually cause cancer. And so to accomplish this objective, they examined dose response studies and on laboratory rats, which were exposed to different concentrations of PCBs. And they also examined retrospective studies of cancers that workers that were employed by these industries had. Next, they had to determine what concentrations people might actually experience. So to accomplish all this, scientists examined data on current concentrations that were actually in the air, the soil, and the water, and they considered the half-life of these PCBs and of this chemical. Because PCBs were found throughout the environment and because they're very persistent, the probability of coming into contact with these PCBs was considered relatively high. And they also considered the potential route of exposure, like eating contaminated fish or drinking contaminated water or just basically breathing contaminated air. The final result of this risk assessment on PCBs showed that the risk from eating contaminated fish is higher than the risk from drinking contaminated water and much higher than breathing contaminated air. As a result, signs were posted on the Hudson River at Silver Lake instructing people to basically not consume the fish there that were caught. So with limited fish consumption, the EPA concluded that the absolute risk of an individual developing cancer from this PCB exposure was quite low. Interesting, right? Like, just stop eating fish. Okay, now you're safe. However, the risk was high enough to cause the EPA to recommend dredging the river and basically removing a large fraction of all the PCBs that had been settled at the bottom of the river. And we've talked about that before.